Alrighty, so here we are with the 9-3 notes of exponential growth and decay. So first one here is exponential growth. It's our initial equation, and it occurs when a quantity increases by the same rate, which we're going to represent by a lowercase r, in each period, which is going to be represented by time, or t. When this happens, the value of the quantity at any given time can be calculated as a function of the rate and the original amount. So the equation that we're going to be looking for exponential growth of a function, and it has the form of y equals a times 1 plus r, and that thing in parentheses is raised to the t. All right, each of these has its own meaning. So we have a y value, an a, an r, and a t that we need to define. So y represents the final amount. So if you're talking about something growing over a 5-year period, y is the final amount, or the end result. A is representing the original amount of whatever it was that you started with. So for instance, if you're investing, it's the amount you start with when you invest, or if you're calculating the growth rate of a population, it's the starting population. Then we have r, which is your rate. And we have to be careful with a rate because the rate is a decimal. Okay, so for example, if you have a rate of 5%, you're actually going to need to write that as 0.05. If you have a rate which is very common, of something like 7.5, they love to put decimals in your percent, that's going to be 0.075. So just be careful. Pretty much you're just moving the decimal that would originally be here after the 5, 2 to the left, or here between the 7 and 5, 2 to the left. And then t represents your time. All right. So we're going to use this equation in this example here. So the original value of a painting is $9,000, and the value increases by 7% each year. We're going to write an exponential growth function to model this situation, and then once we write it, we're going to find the painting's value after 15 years. So first thing that we need to do is write the equation. So if we take a look at the equation again, which is y equals a 1 plus r to the t. Remember that we're trying to find y, or the ending result. So instead we need to figure out what a is, and a is 9,000, the original amount of the painting. Our r is 7%, but remember that 7% is going to be written as 0.07. And then our t is time. And you might think that the time should be written as 15 years, but if we are starting out, sorry, the cat decided to play with a paper airplane. Okay, so if we're starting out writing an equation, we do not want to actually put 15 in for time. So just to write the function, all right, so just to write the function, we're going to have a y, and it's going to equal 9,000 and 1 plus 0.07 to the t. So this is our our function. Then when we are trying to find out what happens after 15 years, that's when we take that equation and plug in a 15 for the t. So we're going to find y after 9,000 times 1 plus 0.07 to the 15. From the order of operations, the first thing you're going to want to solve is this thing that is equal to the power, or sorry, that has a power of 15. So in our calculator, we're typing in that we have 1 plus 0.07. And so, of course, 1 plus 0.07 is going to be 1.07. And then to the 19th. So if that's raised to the 19th power with a little caret, you're going to get 3.6165. So then we'll take that number and multiply by 9,000. So the answer times 9,000. And we realize that if you had a value of a $9,000 painting at 7% increase per year, you are going to have a, after 15 years, a painting that is worth a lot of money. In fact, $32,548.75. That is a lot. Okay. Again, this is the function. Has a independent and a dependent variable that don't have numbers in them. And then once we plug in the 15, now we have our answer. All right, so that's your exponential growth. We have another example here. A sculpture is increasing in value at a rate of 8% per year, and its value in 2000 was $1,200. And we need to write an exponential growth function to model this situation and then find the sculpture's value. So again, we're using our equation of growth. So we have a times 1 plus r to the t. In this scenario, our a value, or the starting value, is $1,200, and the rate is 8%, but again, 8% is actually 0.08. So if we want to write the function, all we need to do is put in each of those pieces, because notice it says write a growth function, and then find the sculpture's value. So we're going to have a function of an a value of 1,200 times 1 plus our r value, 0.08, and that's being raised to the t. So this is the function. Notice there's a y, there's a t, and we don't plug those in yet. Then if we want to solve the equation for the year 2006, remember that the year 2006 is actually going to represent a t of 6, because we're taking 2006 and subtracting the year 2000 when the price was mentioned, and so we'll have 6 for our t. We're not going to plug in 2006. That would make this a very nicely priced painting. So, sculpture. So in that case, we're going to plug in 12,000, 1 plus 0.08, and we're going to have it raised to the 6th power. So again, evaluating this addition there with a power means that we'll have 1.08 to the 6th. And so we'll have 1.5869, and that's going to be multiplied by 12,000. Or sorry, 1,200. And so the value of that painting is $1,904.25. So it gained, after 6 years, it gained about $704.25. All right. The next equation that we're going to have is compound interest. So there's these ideas that what happens is, instead of having your interest compounded per year, which is what we just did, or whatever it is that you're looking at for your rate, it would be taken once a year. What they've tried to do to get you more money, or to make you pay more money, is to have your interest compounded at multiple times per year. So compound interest usually has to do with money. So if we look at filling in this, your compound interest is earned or paid on both the principal, which is the initial amount invested, and previously earned interest. So what happens is, if you earned money from having the interest given to you the first time in the year, then you're going to earn interest on that interest that you just got. So anyway, earned interest is the amount paid by the bank. So when we look at the formula that we're going to be using, we have A for the amount that we have earned, and it's going to equal P times 1 plus a fraction of your rate over N, and that's going to be raised to the power of N times T. So we do need to figure out what each of these values represent. So we've got an A, a P, an R, an N, and a T. The A represents the balance. Again, we're most likely talking about money here. P represents the principal or the original amount of money. R represents the annual interest rate, expressed again as a decimal, as we did in the previous problems. And N represents the number of times the interest is compounded per year. The number of times the interest is compounded per year. We'll go over kind of how you can determine that value in a second, but that is its definition. And then T represents time in years. All right. So breaking down this N value a little bit more, what happens is you're going to get words like annual, quarter, and monthly. So we've got annually, quarterly, and monthly. And what happens is quarterly, there's an R and an L and a Y. Anyway, annually means that that's happening once per year. So if you ever had an annual, birthday, for instance, that's happening once a year. So that means that you're going to put in an N value of 1. And that's actually would revert this entire equation back to what we had as our growth equation. So then we have quarterly, and so that means that it's going to happen 4 times per year, and so that means that our N would be 4. Monthly would make our N 12. We could have daily for 365, but the idea is that that key word is going to transfer into a number of times per year. So taking a look at our first our first example, we're writing a compound interest function to model each situation. So just as we did in the other examples, we want a function that has the variables in it, and then we can plug in some of the pieces. So the first thing they give us here is that there's $1,200 invested at a rate of 2% compounded quarterly. So remember that our formula is going to be P times 1 plus R over N to the NT. Which means that the A we don't know, that's kind of like our Y value. The T we don't know, except that we're going to find it after T years. So once we actually plug it in, then we'll put in a 3. So A and T are going to remain A and T in this formula so that we can have a function and not just an answer. So in that case, we need to find out that P, remember, is named as the principal or the original amount. So in this case, that's going to be 1,200. Then we have our R, which is our rate. And remember that we're not going to put in a 2 because 2 is actually going to represent 0.02. And then we have our N, which notice it says quarterly, and so that means 4. So we're going to take each of these pieces and put it into the original equation, and that's going to be our function. And so the function is going to be this 1,200 that starts 1 plus the fraction of 0.02 over 4 to the 4 times t. So this is our function that we'll be able to plug in the 3 years. So then we're going to find the amount after 3 years. And so we're plugging in 1,200 times 1 plus 0.02 over 4 to the 4 times 3. So we're going to do each of these steps as we go, following the order of operations. So first thing we're going to do is what's inside of the parentheses. Okay, so that means that I'm going to keep the 1200, but I'm going to change this fraction into its decimal equivalent. So 0.02 divided by 4 leaves you with 0.005. All right, the next one is going to be adding each of these two, because again, parentheses in PEMDAS is first. So we're doing parentheses. So 1,200 times 1 plus, so 1.005 is the addition of that. Then after parentheses, we need to do exponents. So if you rewrite this exponent, it's instead of 4 times 5, it'll be 20. And then finally, we can go ahead and actually raise this 1.005 to the 20 power. So 1.005 to the 20th is going to multiply by 1.1049. And if we take 1,200 and multiply by 1.1049, we're going to get the estimated value of $1,325.87 after 3 years. So again, they invested $1,200, and then after 3 years of having the money sit there, not doing anything to it, they will get $125 more, which for doing nothing is an excellent payment. All right. The next equation that we're going to talk about is our exponential decay. This is actually the same as our exponential growth, only of course what's happening to the values is that they are decreasing. So instead of, for instance, a population growing, maybe a population is decreasing, or a value of a painting is decreasing, or a value of a car or something. So in that case, our formula is going to be y equals a1 minus r to the t. And so hopefully that very much looks like our original growth formula. The only difference is this subtraction sign. The values are going to be the same. We have y, a, r, and t. And y represents your final amount, as it did before. A represents your original amount of whatever is going to start decreasing or decaying. And the r is the rate of decay, or the decimal version of that, of course. And then t is going to represent your time. All right, so trying out the exponential decay idea. You have an example. The population of a town is decreasing. There it is, at a rate of 3% per year. So we know that we are going to be using the equation that we just wrote down, which was a1 minus r to the t. The rate there is 3%, and so we're going to have 3%, or technically 0.03. It says in 2000 there were 1,700 people, so that's our starting amount. And we need to write an exponential decay function to model what happens in 2012. So remember that eventually we'll be plugging in a t value of whatever 2012 minus the year 2000 when this equation started. So we'll plug in a t of 12. But to get our function, we're going to keep the y and we're going to keep the t, because those are the two independent and dependent variables. And then we're going to plug in our a of 1,700 and our r of 0.03 and raise that to the t. So this is our function, but then of course we're going to evaluate our function at the number 12 to find out what happens after 12 years. So to solve this, we're going to take 1,700 and end up multiplying by 1 minus 0.03, and that raised to the 12. And so you get 0.6938. And so that multiplied by 1700 or 1700 leaves you with 1179.53. And of course, we are talking about people, so population really can't be 1179.5, so we'll do 1180 since it says 0.5. And again, double checking that our equation worked. We did actually go down in population, so it was doing the correct movement. All right. Then we have our last idea, which is half-life. Basically, it's just saying that the rate that you are given is going to be 0.5 or half. So our official definition is half-life of a substance is the time it takes for 1/2 of the substance to decay into another substance. This is a specific example of decay on this next one here. Again, you could have quarter life or whatever it is, but a lot of times elements will decay, and so this is kind of referencing that. So your half-life talks about an amount, and an amount is going to have to happen after an initial population is multiplied by a rate of 0.5, because again, we're doing half-life, and that 0.5 is being raised to the t. So we have an A, a P, and a T. Notice we don't have an R because we already put that into the formula every time for half-life as 0.5. So A is going to represent your final amount of whatever the element is. P represents the original amount or the initial amount. And then T is going to represent the number of half-lives in a given time period. So we'll go over what that means in our next example. But the idea is that if the half-life is 10 minutes and they want it in an hour, then you're going to have 6 of them. So T might be 6 instead of 1. All right. So here's our science application. We've got astenine, super 218. There tends to be these numbers with like dashes in them as our elements. So anyway, this element has a half-life of 2 seconds, and we need to find the amount left from a 500-gram sample after 10 seconds. So the T value here is tricky because, again, every 2 seconds is a half-life. So that means that we're going to take the 10 seconds that they're giving us and divide it by the 2-second half-life. And so now we know that there are 5 of these half-lives within this problem. So our T is 5. The P value, the original amount, is 500. And so we're going to put that into our equation. So the equation, remember, is A equals P 0.5 to the T. So we're going to plug in a P of 500. And our T is 5. And so we'll raise 0.5 to the 5. And get 0.03125. And multiply that number times 500. And we're going to get 15.625. And 15.625 is the number of grams that are left after 10 seconds. So that thing is decreasing pretty darn fast. All right. So that's our 9-3 exponential growth and decay lesson. So hopefully you can apply that to some problems in the homework.